Hi, I'm Ms. Constantine, and today I would like to introduce you to my new project. It will be a CNC machine based on aluminum profile. In this video, I will try to cover all the details of the design and share my thoughts on it. So, let's begin. The classic gantry scheme was chosen, but with slight modifications. The machine is made mainly for machining soft metals, with cutters up to 6 millimeters in diameter. The working area will be 550 millimeters in the x-axis, 410 in the y-axis, and 150 millimeters in the z-axis. A few words about the components. There will be 15 millimeter linear guides on all axes. I plan to use THK SSR 15 or SHS 15 series. These guides have cages and provide smoother movement with low vibration. The ball screws will also be 15 millimeters on all axes. On the x and y axis with a screw pitch of 10 millimeters, and on the z-axis with 5 millimeters. Delta A 3 series servo drives will be installed on the z-axis, possibly with a brake. It will be clear then. I will put it all together. The spindle will be 2 kilowatts, 80 millimeters in diameter, with auto tool change and the ISO 20 taper. There are two versions of these spindles, with 24K or 36K RPM. Of course, I would like a higher speed spindle, but there appears the need for a higher frequency converter. I have a suitable one for the 24K spindle, but none for the 36K. The higher speed spindle is more expensive, and plus the converter would need to be added to it as well. So no decision on that yet. The control will be Linux CNC. I would like a 7i76E controller. They are not available yet, but I hope that by the time the turn to build the electronics will come, they will appear. So let's take a closer look at the construction. The base of the machine is a welded structure made of 50 millimeter square steel pipe. This is probably the only part that will have to be outsourced, as I do not have the space and skills for such work. Therefore, I tried to make the construction as simple as possible. The machine itself will stand a little below the level of the doors. This should give space for chips and trays. Between the machine and the base will be vibration decoupling. There will also be vibration supports at the bottom of the base. I added diagonal ribs to reduce vibration and rocking when working, because even such a light machine can easily rock such a base, if it is without ribs. It would be good to fill the inner cavities of the pipes with something like polymer concrete, but a lot of things will be attached to them, and it is difficult to provide where exactly. So I will leave it as it is and hope that vibration isolation and its own stiffness will be enough not to listen to the ringing of these pipes. Now let's take a look at the machine itself. The base of the machine is made of an aluminum rectangular profile, 80 by 40 millimeters, with a wall thickness of 5 millimeters. Why did I use this profile instead of the usual profile with T-slots? It's all about rigidity. If we compare two profiles of the same cross-section and approximately the same weight, we will see that this profile is much stiffer, and this applies to both bending and torsion. For a profile with T-slots to be equal in stiffness, it should be much larger, heavier, and more expensive. The only inconvenience with such a profile is that it is more difficult to assemble it, basically more work to mark and make all the threads. But, in my opinion, a little more time during assembly is compensated by better qualities for the whole life cycle of the product. That is why I often use this profile in my designs. The table, on the other hand, is made of a profile with T-slots. I think that this choice is obvious, although it was possible to make a plate for the whole area with a grid of threaded holes. I have worked on a machine with this type of table. It has its pros and cons. But on this machine, I decided to use a conventional T-slot. The portal beam is also a rectangular profile, 120 by 80 millimeters, with a wall thickness of 6 millimeters. It has the same reasons as the base, more rigidity than the profile with T-slots. The portal columns are made of 20 millimeters aluminum. The ribs are 16 millimeters. The ribs are specially placed outside because the entire internal volume between the columns is the working area. This arrangement provides several advantages. First, it is possible to level the entire table by the machine itself without creating a pit. Second, smaller base width and greater resistance to portal tilting. Third, as a result of the second point, since the gantry's tilt rigidity is higher, it is possible to use only one screw in the middle instead of two screws on the sides. Fourth, the portal column beam lies on the portal columns instead of being clamped between them, which removes tight linear tolerances, and it is possible to use free dimensions, which greatly simplifies and reduces the cost of beam machining. There is a downside to this design too. Since the entire surface of the table is on the working zone, the clamps will reduce the zone, but it will be relevant if the workpiece will be on the entire working area. I do not expect a lot of workpieces on the entire working field. So for me, it will not be very important, but there are solutions to this problem. You can use pit bowl type clamps to minimize this difference, or mount the workpiece through if possible, or glue it. These methods will minimize this disadvantage. Now let's look at the Z-axis. The basis of this axis is an aluminum U-shaped profile, which has dimensions of 160 by 65 millimeters and a thickness of 16 millimeters. The rails are located on the profile, and the carriages with the spindle move. This scheme also has its pros and cons. The main advantage is the possibility to use the entire clearance under the portal as a working volume. This is achieved by the fact that the Z-axis travel is larger than the gap under the gantry. I plan to use milling cutters no longer than 60 millimeters, and this difference between the stroke and the clearance allows the cutter to move over the workpiece of maximum height. Since the main part of the work will be on the table, I have selected the lengths and location of the main elements, so that in the lowest position, the carriages of the Z-axis were opposite to the carriages located on the gantry beam. This is the mode of maximum rigidity. The higher the position of the axis, the less rigidity there will be. This problem is partially solved by ribs, but this is not a big problem for me. Such high parts will be rare, and it will be possible to reduce the machining modes. But if it would be necessary to make most of the high parts, it would be better to leave the carriages on the profile and move the rails with the spindle. One of the main requirements was the creation of a cabinet around the machine to minimize chip spillage. Trays and a chip drawer were provided for easy cleanup. I don't plan to use any liquid, most likely just air for cooling or at most an oil mist. So the chips will be dry, and I don't need to make a complicated filtration system and seal the entire work area. The cabinet itself is assembled from 30 T-slot profile. It will open upwards, so there will be maximum open space for comfortable work. The trays at the bottom of the machine will be aluminum or stainless steel, 1 millimeter thick. They are configured in such a way that the maximum amount of chips goes directly into the drawer below. The drawer itself will also be made of aluminum profile and the same sheets on the outside. There will also be a control panel on the cabinet. It will be adjustable in height, tilt, and rotation. The electronics box will be located here. So far, I've made a standard one that fits the dimensions, but it's a little small. Theoretically, it seems to fit everything, but practically trying to fit it will be quite tricky. Servo packs and the frequency converter will be at the bottom, and on top of the two DIN rails, and leave a small space for the servo pack of the fourth axis. The computer and controller will have to be placed on the door, but I may still have to make a custom larger box for the electronics. The cables will go in from the top. In general, the cable tow line will be under the table. I refuse to place it next to the table. Of course, pulling cables under the table will be quite difficult, but we get the advantage that it will always be clean from chips. Because this channel is located below the cutting zone, it always gets the most chips. And even sealed cable tow line are not tight enough, and will eventually let enough chips in to damage the insulation on the cables. And the constant cleaning is pretty annoying. By placing it under the table, I plan to get rid of this problem. A separate mention should be made of the spindle water cooling system. Since I always try to make as clean looking as possible, I usually put standard 120 or 240 aluminum radiators with fan and pumps directly on the gantry or on the Z-axis. But in this machine, I decided to use a different solution, namely to make a passive radiator and install it on the gantry beam. This is a very unusual decision, and it will be a technological adventure in general, but I am willing to do it. To simplify the piping, I designed a distribution part combined with a reservoir and a place for the pump. This idea appeared after making custom distro plates for computer water cooling system. They are very space-saving and look very clean. The radiator itself has a channel for the liquid. As a result, we get a fanless compact system in which you can use a micro pump. If everything works as planned, I think this could be a new option for spindle cooling. Since I plan to use a spindle with auto tool change in this machine, the main question is how exactly to realize this. I will tell you some of my thoughts on this topic. The simplest variant, the tool is changed manually. It will be pre-measured, and such a solution will still reduce the time to change the tool. Compared to a conventional spindle, the disadvantages are obvious. You will have to be distracted all the time to change tools, especially on short programs. And there is a possibility of mistaking the tool. Therefore, I did not consider this option. The next solution is to use a linear magazine. It is still quite simple, but the main disadvantage is that such a magazine occupies the working field of the machine. I wanted to keep it as large as possible, so I smoothly moved on to the next option, a carousel. This is probably the most common solution for organizing a tools magazine. The advantage of this design is that most of the carousel is located outside the machine and occupies a minimum of the working field. There are also cons, a much more complex design, a gearbox, motor, sensors, and all this needs to be controlled somehow. Programming all this so that the tool change is done automatically is also quite difficult. But the main disadvantage for me was that on this machine, the size of the carousel is strictly limited. In my case, between the portal columns and the machine cabinet was 400 by 250 millimeters. I could not make it go beyond that. In this case, the carousel was limited to the short side, and only 8 tools were possible. On the one hand, 8 tools is not so small, and will allow to make quite complex parts. On the other hand, 12 or 16 tools are much better, because they allow you to keep the most frequently used 8, 10 tools in the magazine all the time, and change the rest as needed. In my opinion, this scheme is much more comfortable to work with. At last, I decided to try to design a chain tool magazine. It can be any shape, not just round, and I managed to place as many as 18 tools. The complication was not too great compared to carousel-type magazine. Only the chain mechanism itself was added. Let's take a closer look at it. The drive is carried out through a worm gearbox. It was chosen for layout reasons. The motor is installed NEMA 17 stepper, but perhaps I will replace it with a servo drive, 100 watts. Chain and 4 sprockets make up the moving part of the mechanism. Also installed sensor of the initial position of the magazine, and the sensor of the passage of each tool. There is also a sensor for the presence of a tool in the magazine to prevent an attempt to install a tool in an occupied cell. I added a small pneumatic cylinder for the sliding door. I'm thinking of making the case transparent to show which tools are installed. I have never designed such mechanisms, and maybe there are mistakes here, but at first glance, everything should work well. This is how the machine should turn out. As in any project of such complexity, here is a large set of compromises. And I hope that I was able to tell about all the interesting points and why I chose these solutions and not others. Now all that's left is to start the build itself. I hope to be able to show you a working machine in the near future.